This is the 2019 MEXT College of Technology Mathematics paper. Let's begin. Section 1, Number 1. If a cubic function has a constant term, we should consider its factors. So plus 2 is either plus 1 times plus 2 or minus 1 times minus 2. So let's see what happens when we substitute x equals 1. So the left-hand side matches the right-hand side. That means that x minus 1 is a factor. This implies that x minus 2 is also a factor. X minus 1 times x minus 2 is x squared minus 3x plus 2. So let's divide this cubic function by this quadratic function to find the remainder. X times x squared is x cubed. X times minus 3x is minus 3x squared. X times 2 is plus 2x. Minus 2 minus minus 3 is 1. Minus 1 minus 2 is minus 3. This is exactly the same as this, so we have plus 1. So now we know that this cubic function can be factorized as x minus 1 times x plus 1 times x minus 2. So the solutions are x equals plus and minus 1 and plus 2. Section 1, Number 2. First of all, let's factorize the left-hand side of this equation. So from this we know that cosine x is equal to 0, or 1 minus 2 cosine x equals 0. If the angle is between 0 and pi, cosine x becomes 0 when x is pi over 2, or 90 degrees. Next, let's transform the second equation. Cosine x is equal to 1/2 when x is equal to pi over 3, or 60 degrees. Therefore, x is equal to pi over 3, or pi over 2. Section 1, Number 3. Recall the definition of absolute values. Given the absolute value of a, if a is greater than or equal to 0, then the absolute value of a is a. If a is less than 0, then the absolute value of a is minus a. So we basically have to find out whether these two parts are greater than or less than 0. First, root 8 is 2 root 2, which is 2 times 1.4 something, which is about 2.8 something. So root 8 minus 3 is less than 0. Likewise, 2 minus root 2 is 2 minus 1.4 something, which is greater than 0. So, as for the first part, we can remove the absolute value signs by putting a minus in front. As for the second part, we can simply remove the absolute value signs. So the answer is minus 3 root 2 plus 5, or 5 minus 3 root 2. Section 1, Number 4. Let's express the right-hand side in terms of log base 2. To do so, let's use the change of base rule. The new base can be any arbitrary number, but for the sake of convenience, let's choose base 2. Now, 4 is 2 squared. The exponent can be moved to the front, and log base 2 of 2 is 1. So this is equal to 1/2 times log base 2 of x minus 1. And let's move the 1/2 back to the exponent. Now that we have the same base, we can just compare x minus 1 and root x minus 1. a is equal to root a if a is either 0 or 1. X minus 1 is 0 implies x is 1, and x minus 1 equals 1 implies x is 2. If we assume the former case, then we would have log base 2 of 0, which is not allowed. So x must be 2. Section 1, number 5. First of all, the second term in this function is a little hard to work with. So let's use the angle addition formula to rewrite this part. Cosine x plus pi over 3 is cosine x times cosine pi over 3 minus sine x times sine pi over 3. So cosine pi over 3 is 1/2, and sine pi over 3 is root 3 over 2. So now we have f of x equals cosine x plus 1/2 times cosine x minus root 3 over 2 times sine x, which is 3 over 2 cosine x minus root 3 over 2 sine x. Next, let's differentiate this function. F dash of x is minus 3 over 2 sine x minus root 3 over 2 cosine x. And let f dash of x be equal to 0 to find the maximum and minimum values. Divide both sides by cosine x. Sine divided by cosine is tangent. Now, tangent is equal to minus root 3 over 3 when the angle is 5 over 6 pi or 11 over 6 pi. So let's substitute these values of x into the original function. This is equal to minus root 3, and this is equal to positive root 3. So the maximum value m is root 3, which is obtained at x equals 11 over 6 pi. Section 1, number 6. So this question specifically says you have to use this expression, but I ended up solving it without using it. So first of all, let y be equal to this expression, and let's take the natural log of both sides. We can move the exponent to the front, and here we can use L'Hopital's rule, which basically says that if we have a function on the numerator and another function on the denominator, we can differentiate them. So what is the derivative of the natural log of 1 plus 2h? Derivative of the natural log of the function f of x is equal to f dash of x over f of x. So this is equal to 2 over 1 plus 2h. And the derivative of h is just 1. So we have 2 over 1 plus 2h. As h approaches 0, 2h becomes closer and closer to 0. So this is equal to 2 over 1 plus 0, which is 2. So the natural log of y is equal to 2. Since ln is log base e, y is equal to e squared. So this is equal to e squared, and this is the final answer. Section 1, number 7. We have a plane in 3D, so let's try to express y and z in terms of x. So y is x plus 2 over 3, and z is x plus 3 over 2. Now let's substitute these values of y and z into this equation. X is equal to minus 11. Now substitute this value of x into the equation for y. So y is minus 3. And finally, let's substitute this value of x into the equation of z. So z is minus 4. So these are the answers. Section 1, number 8. In order to find the equation of the tangent, let's differentiate y. So let's define the coordinates of the point of tangency. Let's call it x-coordinate, x sub 1, and its y-coordinates, log base e of x sub 1. And let's call this point P. At P, dy dx is 1 over x sub 1. And this is the slope of the tangent, and since the tangent line goes through the origin, the equation of the tangent must be y equals 1 over x sub 1 times x. At P, y is equal to log base e of x sub 1, x is equal to x sub 1. So log base e of x sub 1 is 1. This implies that x sub 1 must be e, because log base e of e equals 1. Therefore, the equation of the tangent line is y equals 1 over e times x. Section 1, number 9. Let's decompose this fraction into partial fractions. P times n plus 2 plus q times n. P times n plus 2 plus q times n is equal to 1. To eliminate q, let's assume that n is 0. Then we have p times 0 plus 2 equals 1. So 2p is 1, therefore p is 1/2. Next, let's assume n is minus 2. Then we have minus 2q is 1, meaning that q is minus 1/2. And let's substitute these values into the left-hand side of this equation. So this is equal to 1/2 times sigma As you can see, all the terms except 1 and 1/2 will be eliminated. So this is the final answer. Section 1, number 10. So in this question, we have to evaluate the limit of this expression as x approaches negative infinity. So because x is approaching negative infinity, we are only considering the negative values of x. When x is negative, the absolute value of x is minus x. And let's also recall that the absolute value of x is the same as root x squared. So we're going to divide both the numerator and the denominator by the absolute value of x. According to the first definition, the absolute value of x when x is negative is minus x. And according to the second definition, the absolute value of x when x is negative is root x squared. And root x squared is, of course, x. As x approaches negative infinity, 1 over x becomes closer and closer to 0. So the answer is minus 2. Section 1, number 11. recall that log base a of b over c is log base a of b minus log base a of c. So log base e of root x minus 1 over x plus 1 is log base e of root x minus 1 minus log base e of x plus 1. And root x minus 1 is x minus 1 raised to the power of a half. And the exponent can be moved to the front. And now we are ready to differentiate this function. Recall that the derivative of the natural log of f of x is f dash of x over f of x. So f dash of x is 1/2 times 1 over x minus 1 minus 1 over x plus 1. So this is the final answer. Section 1, number 12. First of all, sine 3x is very difficult to work with. So let's rewrite sine 3x. Remember that sine 3x is equal to 3 sine x minus 4 sine x cubed. Therefore, sine 3x times sine x is 3 sine x squared minus 4 sine x raised to the 4th power. 3 times sine x squared minus 4 times sine x raised to the 4th power. And don't forget dx. Let's work with the first part. Recall that sine x squared is equal to 1/2 times 1 minus cosine 2x. The integral of 1 is x. What is the integral of cosine 2x? 1/2 times sine 2x. Now, sine 2 pi and sine minus 2 pi are both 0, so the first part is equal to pi. Let's move on to the second part. Sine x raised to the 4th power is sine x squared squared. Sine x squared is 1/2 times 1 minus cosine 2x. So sine x raised to the 4th power is 1/2 times 1 minus cosine 2x squared. And this is equal to 1/4 1 minus 2 cosine 2x plus cosine 2x squared. Cosine x squared is 1/2 times 1 plus cosine 2x. So cosine 2x squared is 1/2 times 1 plus cosine 4x. So this is equal to therefore, remember that the integral of cosine 2x is 1/2 times sine 2x. 2 times 1/2 is 1, so we have sine 2x. What is the integral of cosine 4x? This is 1/4 times sine 4x. 1/2 times 1/4 is 1/8. Sine 2 pi and sine minus 2 pi are both 0, and sine 4 pi and sine minus 4 pi are also 0. And I forgot to write 1/4. So the second term is equal to 3 over 4 times pi. Therefore, 3 pi minus 4 times 3 over 4 pi, this is equal to 0. So the answer is 0. Section 2, number 1. In this question, we're given a matrix and we need to express a raised to the nth power. So first of all, let's see what happens when a is squared. So we start with first row, first column. 1/2 times 1/2 is 1/4. 1/2 times 0 is 0. First row, second column. 1/2 times 0 is 0. 0 times 0 is 0. Second row, first column. 0 times 1/2 is 0. 0 times 0 is 0. Second row, second column. 0 times 0 is 0. 1/2 times 1/2 is 1/4. So as you can see, a raised to the nth power, 1/2 raised to the nth power, 0, 0, 1/2 raised to the nth power, which can be expressed like this, if you wish. Section 2, number 2. So based on the pattern that we observed in the previous question, we know that we get a geometric sequence like this, where the common ratio r is 1/2. What is the formula for calculating the sum of a geometric sequence? So in this case, a, the initial term, is 1/2. The common ratio is 1/2. Therefore, this sum is equal to 1 minus 1 over 2 raised to the nth power, 0, 0, and 1 minus 1 over 2 raised to the nth power. Section 2, number 3. In this question, we need to find the inverse of the sum s. Using this formula, the inverse of s is a times d minus 0 times 0, which is 0, times swap a and b and change the signs of b and c. We can multiply each element in this matrix with this number. And if we multiply these two expressions, we get 1 divided by 1 minus 1 over 2 raised to the nth power. So this is the final answer. Section 3, number 1. So first, notice that sine x cubed is sine x squared times sine x, and sine x squared is 1 minus cosine x squared. Now, we can try integration by substitution. Let u be equal to cosine x, which means du is minus sine x. And from this, we get dy equals du over minus sine x. So let's substitute these values. So we have 1 minus u squared times sine x times du over minus sine x. So this is equal to u squared minus 1 du. Now let us integrate. Recall that u is cosine x. Cosine pi over 2 is 0, whereas cosine 0 is 1. So the answer is 2/3. Section 3, number 2. So notice that we have reciprocals, 2k, 2k, 2k minus 1, 2k minus 1, and so on. All these numbers disappear except 2k plus 1 in the denominator and pi over 2. So the left hand side becomes pi over 2 times 1 over 2k plus 1. Therefore, a sub k is equal to 1 over 2k plus 1. Section 3, number 3. Similar to the previous question, we have I sub 2k minus 1 times I sub 2k equals pi over 2 times b sub k, and we need to find b sub k. So first, we need to figure out what a sub 2k minus 1 looks like. So looking at I sub 2k plus 1, we see that whatever comes here appears at the denominator of the first fraction, and from then on we just subtract 1. I sub 2k minus 1 times I sub 2k. So once again we have reciprocals except for these two numbers. So we have pi over 2 times 1 over 2k equals pi over 2 times b sub k, meaning b sub k is equal to 1 over 2k. Section 3, number 4. In this question, we need to calculate the limit of this expression by assuming this inequality. So first of all, let's try and rewrite this expression. Inside the curly brackets, we have I sub 2k minus 1, except we don't have 2k. Now, recall that b sub k is 1 over 2k. So 2k is 1 over b sub k. 4k is 2 times 2k, which is 2 over b sub k. And because I sub 2k minus 1 times I sub 2k is equal to pi over 2 times b sub k is equal to 2 over pi times I sub 2k minus 1 times I sub 2k. This is equal to pi times I sub 2k minus 1 over I sub 2k. So essentially, we have to find the limit of pi times I sub 2k minus 1 over I sub 2k as k approaches infinity. Next, let's pay attention to this inequality. First, let's divide each of these by I sub 2k. In the middle, we have 1. And we have an expression here that is identical to this expression. Next, notice that I sub 2k minus 1 divided by I sub 2k plus 1 is greater than I sub 2k minus 1 divided by I sub 2k, because I sub 2k is greater than I sub 2k plus 1. When we have two fractions with the same numerator, the greater the denominator, the smaller the whole fraction is. So, because I sub 2k is greater than I sub 2k plus 1, the fraction on the left is smaller than the fraction on the right. Therefore, we can add this to this inequality. Now, what is I sub 2k minus 1 divided by I sub 2k plus 1? Notice that I sub 2k minus 1 is identical except for this part. So, we have 1 over 2k plus 1, which is 2k plus 1 over 2k. Now, we can use a trick using the squeeze theorem aka the sandwich theorem. Basically, if g of x and h of x have the same limit, then f of x sandwiched between these two functions also has the same limit. The limit of 1 as k approaches infinity is of course 1. Then what is the limit of 2k plus 1 divided by 2k as k approaches infinity? Divide each term by k. Recall that the limit of 1 over x as x approaches infinity is 0. So as k approaches infinity, this term becomes 0. So this is equal to 2 over 2, which is 1. So we have now shown that this function in between is squeezed between two functions with the same limit. Therefore, this is equal to pi times 1, which is just pi. And this is the final answer.